Welcome to this video tutorial on the conservation of energy. Let's begin by defining kinetic energy and gravitational potential. Firstly, the kinetic energy we shall denote to be E with a subscript k. This is going to be equal to 1/2 times the mass of an object times the speed squared. If an object is moving, let's say with a speed 10 meters per second, and it has a mass, then it will have a kinetic energy. And this kinetic energy can be maintained throughout a collision with maybe another object in ideal conditions, or if a ball was to roll up a hill, it can be turned into gravitational potential energy. We shall define gravitational potential energy to be V for now, as we're not working with any other potentials, so we don't need any subscripts. This is going to be equal to mgh, where you have the mass m, g, the acceleration due to gravity, on whatever planet you're considering, and then h, the height that the object sits on from above the 0 point, where we will normally define the 0 point, v equals 0, to be at ground. And therefore, if we have a ball that sits at a height 10 meters above the surface, and we know the mass, and we know the acceleration due to gravity on that planet, then we can give it a gravitational potential. Both energy and potential have the units of joules, denoted with a capital J. So how do we convert between gravitational potential and kinetic energy? Well, in general, energy is conserved, as the title of this video would suggest. So therefore we can say that the initial energy is equal to the final energy. Now this is always true. Not even in ideal conditions, this is true in all conditions. However, in everything but ideal conditions, the energy is going to leak into things that we can't measure. For example, if we had a ball that's rolling down a slope as such, the energy at the beginning of the experiment would be the same as the energy at the end of the experiment. However, some of that sound may have been leaked off due to sound, or maybe some energy may have gone into heating the ball. These are things that's very hard to measure. And so when we say ideal conditions, we typically mean that the energy of the ball in terms of kinetic and gravitational energy is constant, as these are the major factors. If we know that the initial energy is equal to the final energy, then we can pretty much say that the initial kinetic energy, which we will denote as E, K, I, plus the initial gravitational potential energy, is equal to the kinetic final energy plus the final potential energy. Here we have said that the energy of the ball at any point is going to be made up of a kinetic energy and a gravitational energy, which means that this ball at a certain moment might have a speed v, and it might be sitting at a h height from the surface. And so therefore we can say that E is equal to 1/2 mv squared plus mgh if we say the ball has a mass m. And the summation of these two energies or potentials is going to be the same before and after the reaction in ideal conditions, but the values of the kinetic and the potential can muddle around how they want depending on the experiment. During the editing process, I decided that it was a good idea to define a potential with respect to energy. So firstly, both energy and gravitational potential have the same units of joules. But a potential is, as this definition states, is an energy which results from a position or a configuration. So you can see our gravitational potential energy is due to a height, which is acted upon by gravity. And this means that if the ball were to be dropped, this potential energy could be turned into kinetic energy. Let's move on to an animated example. To the left of your screen, you'll see a setup that has a ball that's about to fall onto the surface of the exoplanet TRAPPIST-1d. Our task is to find out, when the rover enables the ball to fall to the ground, what will be the speed of the ball as it hits the ground using only the conservation of energy. We've been told that the ball starts off at a height of 3.6 meters. We've been told to assume that all of the potential energy is converted into kinetic energy. And then we need to find out the speed of the ball when it hits the ground if we've been told the acceleration due to gravity on TRAPPIST-1d is 0.69 g, where g is the acceleration due to gravity on Earth. So we know that the initial energy is equal to the final energy, and then by extension the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. If the ball is at the ground at the end of the experiment, then we can say the final potential is 0, as this is where we define the 0 point to be. And then we can also say at the beginning of the experiment, as the ball is not moving, the initial kinetic energy is also going to be 0, where these values have the units of joules. This leaves us with a very simple expression that Vi is equal to EFK, the final kinetic energy. And then we can say that mgh is equal to 1/2 mv squared. And then this is just a simple equation to solve. We cross out the m's, and then we solve for v, which if you take the time, you'll find out that v squared is equal to 2gh, and therefore v is equal to plus or minus the square root of 2gh. As we're looking for only a magnitude, we will just take the positive value. Next we sub in our values. V is equal to the square root of 2 times g, where we should have been more precise in this example. Here the acceleration on TRAPPIST-1d, and so we should be using g1d in our formulas. Of course, if we were on Earth, then it would just be g. And so we sub in our value of g1d, which is 0.69 multiplied by the acceleration due to gravity on Earth, which is 9.8, and then multiplied by h, which we've been told is 3.6 meters. If you type this into a calculator, you'll find to one decimal place, the answer is 7.0 meters per second. You will note that if you've seen some previous videos, we've actually calculated a lot about this setup using many different methods. But this energy conservation method is one of the most efficient ones that we have used. Secondly, the ball hits the ground with a speed of 6.8 meters per second. We've been told this for sure. And so we need to explain the difference in speeds between this and the one that we calculated previously at 7 meters per second. Well, the answer is most likely to be that if our ball actually has slightly less of a speed at the end, as our kinetic energy is proportional to v squared, this is exactly the same as saying that EK is equal to some undefined constant c multiplied by v squared. We know that if the speed is lower, then the kinetic energy is lower, and therefore in reality EK calculated here is actually less than calculated above. And so what does this mean? We had that the initial potential energy, gravitational potential energy, was equal to our kinetic energy as seen up here. But if our kinetic energy is less than above, then it means there was some other energy, which I'm just going to call gamma for now. Which means that this gamma value was non-zero, which means that we had energy leak from the gravitational potential energy into some other energy. And now, if we think about it practically, what is there going to be in a world like TRAPPIST-1D? Well, there might be something like wind speed, for example, or air resistance. But of course, it could just be down to mathematical error again and not reading our values completely precisely. It's difficult to tell, but typically in an exam question, if you have some sort of excess energy, it's probably going to be one of the three. It's going to be energy lost due to air resistance, it's going to be sound energy, or maybe heat energy. And so depending on the situation, it's likely to be one of the three, or maybe something else. Whatever seems relevant to the question. In this case, air resistance seems likely if it is actually not an error due to calculation. Let's move on to some written examples. A rock of mass 5 kilograms falls from a height of 10 meters on the exoplanet TRAPPIST-1D, where this is the same exoplanet as we had in the previous animation. We know the acceleration due to gravity on this planet, as before, 0.69 g, where g is the acceleration due to gravity on Earth. On collision with the ground, the rock breaks up into 10 identical pieces, and the rock is initially at rest. What is the speed of each of these pieces? We start off by writing down our conservation of energy, which is the initial equals the final energy. Firstly, we define our initial energy to be equal to the kinetic energy of the rock, which we will call big capital R, plus the potential energy of the initial rock, which is going to be equal to just the potential energy of the rock, because we know the rock is initially at rest, and as the kinetic energy is proportional to the speed squared, this would be 0. This is just VR. We also know that the final energy, although it is equal to the sum of the kinetic and the potential energy of the small rocks, we know that there is a collision with the ground, meaning that by the time we're at this final point in our experiment, there's going to be no potential energy because we're going to be sitting on the ground. And so this is just going to be the kinetic energy of the rocks broken up, which we'll call smaller. But notice that there are 10 identical small pieces of rock. So actually, the final energy is going to be 10 lots of this final kinetic energy of one rock. We can then equate the initial and the final energy, giving us VR is equal to 10 EK little r. And so the potential energy of the large rock goes into 10 lots of the kinetic energy of one small bit of rock. Let's sub in our variables. V is equal to m, g, h, where m is going to be of the large rock, capital R, which is going to be equal to 10 lots of 1/2 m of a small rock, m lowercase r, v squared. Once again, lowercase r for the small pieces of rock. This gives us, when we simplify, m capital R, g, and we should state this is for the exoplanet 1D, and same for here. mr g1dh is going to be equal to 5, which is 10 divided by 2, mr vr squared. We wish to find the speed of each of the small pieces, which is v lowercase r, and so now we just rearrange. Firstly, we get that VR squared is equal to m capital R g1d h, all divided by 5mr, which leads on to VR being the square root of all of these things. When we sub in our values, we get the mass of the large rock, capital R, which is 5 kilograms, as stated at the beginning of the question, multiplied by g1d, which from up here is 0.69 multiplied by the acceleration due to gravity on Earth, which is 9.8 meters per second squared, multiplied by the height it was at, which is 10 meters. All of this is then divided by 5 times the mass of a little rock. We know that our large rock broke into 10 identical pieces, which means that our mass of one small bit of rock is 10 times less than our large rock, which is 500 grams or 0.5 kilos. I will quickly cancel out these two 5s, and then you can stick the rest into a calculator. And then this will give you a value of 11.6 meters per second. Which means that when a large rock falls from 8 to 10 meters on this planet and it weighs 5 kilograms, in fact, if it weighs any weight, then when it breaks up into 10 identical pieces, it will actually, all of the pieces will have this speed. Notice I say any mass, because it turns out the mass in this question is actually somewhat of a red herring. It's not needed. Because as you can see from this formula here, if we copy it again over here, but instead we say that m little r is actually m large R over 10, and then it turns out that when we sub m little r into this equation, we get v squared r is equal to mr g1d h over 5 m capital R multiplied by 10 on the top, meaning that the mass cancels, meaning that VR, where r is our lowercase r, is actually independent of the mass of the rock, and so therefore is not needed. Let's move on to part 2. The same rock is dropped from the same height. However, this time 0.1% of the energy on the collision is converted into sound energy. Calculate the amount of sound energy. How high would the rock have to be dropped to release 1 joule of sound energy? This time we've been told that 0.1% of the energy on the collision is converted into sound. Well, how much is this? We can work with either side of the equation. We know that VR is equal to 10 EK little r. And so either side of this equation is the amount of energy on the collision, because energy is conserved. But this is not true anymore for this question, because now we've been told that we have an additional factor, which I'm going to call E subscript S for the sound energy. And we've been told that ES is equal to 0.1%, which is actually 1 over 1000 multiplied by the energy before the reaction, which is V capital R. And therefore it is equal to 1 over 1000 M capital R G1D H. If we sub in all our values, we get 5 multiplied by 0.69 multiplied by 9.8 multiplied by 10, all divided by 1000. And we'll get the ES is equal to 0.34 joules, 2 decimal places. And then the second part of this question is how high would the rock have to fall to release 1 joule of sound energy? This is very simple. We simply take our equation that we had before, which is ES is equal to mr g1dh all over 1000, and then rearrange for the h, which is h is equal to 1000 ES over mr g1d, and sub in our values of 1000 multiplied by our now 1 joule of sound energy divided by 5 multiplied by 0.69 multiplied by 9.8. And this will give you that h is equal to 29.6 meters, which means when 0.1% of the collision energy is turned into sound energy, in this case, to release 1 joule of sound energy, the rock would need to be dropped from a height of 29.6 meters. Thank you for watching this video tutorial. Visit my website coherentphysics.com for many examples with fully worked solutions.